Chapter 3. Functions. People think that computer science is the art of geniuses, but the actual reality is the opposite. Just many people doing things that build on each other, like a wall of many stones. Donald Knuth. Functions are one of the most central tools in JavaScript programming. The concept of wrapping a piece of a program in a value has many uses. It gives us a way to structure larger programs, to reduce repetition, to associate names with subprograms, and to isolate these subprograms from each other. The most obvious application of functions is defining new vocabulary. Creating new words in prose is usually bad style, but in programming it is indispensable. Typical adult English speakers have some 20,000 words in their vocabulary. Few programming languages come with 20,000 commands built in, and the vocabulary that is available tends to be more precisely defined and thus less flexible than in human language. Therefore, we have to introduce new words to avoid excessive verbosity. Defining a function. A function definition is a regular binding where the value of the binding is a function. For example, this code defines square to refer to a function that produces the square of a given number. A function is created with an expression that starts with the keyword function. Functions have a set of parameters, in this case only x, and a body, which contains the statements that are to be executed when the function is called. The body of a function created this way must always be wrapped in braces even when it consists of only a single statement. A function can have multiple parameters or no parameters at all. In the following example, makeNoise does not list any parameter names, whereas round2, which rounds n to the nearest multiple of step, lists 2. Some functions, such as round2 and square, produce a value and some don't, such as makeNoise, whose only effect is a side effect. A return statement determines the value of the function returns. When control comes across such a statement, it immediately jumps out of the current function and gives the returned value to the code that was called the function. A return keyword without an expression after it will cause the function to return undefined. Functions that don't have a return statement after all, such as makeNoise, simply return undefined. Parameters to a function behave like regular bindings, but their initial values are given by the caller of the function, not the code in the function itself. Bindings and scopes. Each binding has a scope, which is the part of the program in which the binding is visible. For bindings defined outside of any program, block, or module, see Chapter 10, the scope is the whole program. You can refer to such bindings wherever you want. These are called global. Bindings created for function parameters or declared inside a function can be referred only in that function, so they are known as local bindings. Every time the function is called, new instances of these bindings are created. This provides some isolation between functions. Each function call acts on its own little world, its local environment, and can often be understood without knowing a lot about what's going on in the global environment. Bindings declared with let and const are in fact local to the block in which they are declared. So if you create one of those inside of a loop, the code before and after the loop cannot see it. In pre-2015 JavaScript, only functions created new scopes, so old-style bindings created with the var keyword are visible throughout the whole function in which they appear or throughout the global scope if they are not in a function. Each scope can look out into the scope around it, so x is visible inside the block in the example. The exception is when multiple bindings have the same name. In that case, code can see only the innermost one. For example, when the code inside the half function refers to n, it is seeing its own n, not the global n. Nested scope. JavaScript distinguishes not just global and local bindings. Blocks and functions can be created inside other blocks and functions, producing multiple degrees of locality. For example, this function, which outputs the ingredients needed to make a batch of hummus, has another function inside it. The code inside the ingredient function can see the factor binding from the outer function, but its local bindings, such as unit or ingredient amount, are not visible in the outer function. The set of bindings visible inside a block is determined by the place of that block in the program text. Each local scope can also see all the local scopes that contain it, and all scopes can see the global scope. This approach to binding visibility is called lexical scoping. Functions as values. A function binding usually simply acts as a name for a specific piece of the program. Such a binding is defined once and never changed. This makes it easy to confuse the function and its name. But the two are different. A function value can do all the things that other values can do. You can use it in arbitrary expressions, not just call it. It is possible to store a function value in a new binding, pass it as an argument to a function, and so on. Similarly, a binding that holds a function is still just a regular binding and can, if not constant, be assigned a new value, like so. In Chapter 5, we'll discuss the interesting things that we can do by passing function values to other functions. Declaration notation. There is a slightly shorter way to create a function binding. When the function keyword is used at the start of a statement, it works differently. This is a function declaration. The statement defines the binding square and points it at the given function. It is slightly easier to write and doesn't require a semicolon after the function. There is one subtlety with this form of function definition. The preceding code works even though the function is defined below the code that uses it. Function declarations are not part of the regular top-to-bottom flow of control. They are conceptually moved to the top of their scope and can be used by all code in that scope. This is sometimes useful because it offers the freedom to order code in the way that it seems clearest without worrying about having to define all functions before they are used. Arrow functions. There's a third notation for functions which looks very different from the others. Instead of the function keyword, it uses an arrow, made up of an equal sign and a greater than character, not to be confused with the greater than or equal operator, which is written greater than equal to. The arrow comes after the list of parameters and is followed by the function's body. It expresses something like, this input, the parameters, produces this result, the body. When there is only one parameter name, you can omit the parentheses around the parameter list. If the body is a single expression rather than a block and braces, that expression will be returned from the function. So these two definitions of square do the same thing. When an arrow function has no parameters at all, its parameter list is just an empty set of parentheses. There's no deep reason to have both arrow functions and function expressions in the language. Apart from a minor detail which we'll discuss in Chapter 6, they do the same thing. Arrow functions were added in 2015, mostly to make it possible to write small function expressions in a less verbose way. We'll use them often in Chapter 5. The call stack. The way control flows through functions is somewhat involved. Let's take a closer look at it. Here's a simple program that makes a few function calls. A run through this program goes roughly like this. The call to greet causes console to jump to the start of the function line 2. The function calls console log, which takes control, does its job, and then returns control to line 2. There, it reaches the end of the greet function, so it returns to the place that it called, line 4. The line after that calls console log again. After that returns the program reached its end. We could show the flow of control schematically like this. Because a function has to jump back to the place that called it when it returns, the computer must remember the context from which the call happened. In one case, console log has to return the greet function when it is done. In the other case, it returns to the end of the program. The place where the computer stores this context is the call stack. Every time a function is called, the current context is stored on top of this stack. When a function returns, it removes the top context from the stack and uses that context to continue execution. Storing this stack requires space in the computer's memory. When the stack grows too big, the computer will fail with a message like out of stack space or too much recursion. The following code illustrates this by asking the computer a really hard question that causes an infinite back and forth between two functions. Or rather, it would be infinite if the computer had an infinite stack. As it is, we will run out of space or blow the stack. Optional arguments. The following code is allowed and executes without any problem. We define square with only one parameter, yet when we call it with 3, the language doesn't complain. It ignores the extra arguments and computes the square of the first one. JavaScript is extremely broad-minded about the number of arguments you can pass to a function. If you pass too many, the extra ones are ignored. If you pass too few, the missing parameters are assigned to the value undefined. The downside of this is that it's possible, likely even, that you will accidentally pass the wrong number of arguments to functions, and no one will tell you about it. The upside is that you can use this behavior to allow a function to be called with different numbers of arguments. For example, the minus function tries to imitate the minus operator by acting on either 1 or 2 arguments. If you write an equals operator after a parameter followed by an expression, the value of that expression will replace the argument when it is not given. For example, this version of round2 makes its second argument optional. If you don't provide it or pass the value undefined, it will default to 1. The next chapter will introduce a way in which function body can get at the whole list of arguments it was passed. This is helpful because it allows a function to accept any number of arguments. For example, console log does this, outputting all of the values it is given. Closure. The ability to treat functions as values, combined with the fact that local bindings are recreated every time a function is called, brings up an interesting question. What happens to local bindings when the function call that created them is no longer active? The following code shows an example of this. It defines a function, wrap_value, that creates a local binding, then it returns a function that accesses and returns this local binding. This is allowed, and it works as you'd hope. Both instances of the binding can still be accessed. This situation is a good demonstration of the fact that local bindings are created anew for every call, and different calls don't affect each other's local bindings. This feature, being able to reference a specific instance of local binding in an enclosing scope, is called closure. A function that references bindings from local scopes around it is called a closure. This behavior not only frees you from having to worry about the lifetimes of bindings, but also makes it possible to use function values in some creative ways. With a slight change, we can turn the previous example into a way to create functions that multiply by an arbitrary amount. The explicit local binding from the wrap_value example isn't really needed since a parameter is itself a local binding. Thinking about programs like this takes some practice. A good mental model is to think of function values as containing both the code in their body and the environment in which they are created. When called, the function body sees the environment in which it was created, not the environment in which it was called. In the previous example, multiplier is called and creates an environment in which its factor parameter is bound to 2. The function value it returns, which is stored in twice, remembers the environment so that when it is called, it multiplies its argument by 2. Recursion. It is perfectly okay for a function to call itself as long as it doesn't do so often that it overflows the stack. A function that calls itself is called recursive. Recursion allows some functions to be written in a different style. Take, for example, this power function, which does the same as the exponentiation operator. This is rather close to the way mathematicians define exponentiation, and arguably defines the concept more clearly than the loop we used in Chapter 2. The function calls itself multiple times with ever smaller exponents to achieve the repeated multiplication. However, this implementation has one problem. In typical JavaScript implementations, it's about 3 times slower than a version using a for loop. Running through a simple loop is generally cheaper than calling a function multiple times. The dilemma of speed versus elegance is an interesting one. You can see it as a kind of continuum between human friendliness and machine friendliness. Almost any program can be made faster by making it bigger and more convoluted. The programmer has to find an appropriate balance. In the case of the power function, an inelegant looping version is still fairly simple and easy to read. It doesn't make much sense to replace it with a recursive function. Often, though, a program deals with such complex concepts that giving up some efficiency in order to make the program more straightforward is helpful. Worrying about efficiency can be a distraction. It's yet another factor that complicates program design, and when you're doing something that's already difficult, that extra thing to worry about can be paralyzing. Therefore, you should generally start by writing something that's correct and easy to understand. If you're worried that it's too slow, which it usually isn't since most code simply isn't executed often enough to take any significant amount of time, you can measure afterwards and improve if it's necessary. Recursion is not always just an inefficient alternative to looping. Some problems really are easier to solve with recursion than with loops. Most often, these are problems that require exploring or processing several branches, each of which might branch out again into even more branches. Consider this puzzle. By starting from the number 1 and repeatedly either adding 5 or multiplying by 3, an infinite set of numbers can be produced. How would you write a function that, given a number, tries to find a sequence of such additions and multiplications that produces that number? For example, the number 13 could be reached by first multiplying by 3 and then adding 5 twice, whereas the number 15 cannot be reached at all. Here is a recursive solution. Note that this problem doesn't necessarily find the shortest sequence of operations. It is satisfied when it finds any sequence at all. It's okay if you don't see how this code works right away. Let's work through it since it makes for a great exercise in recursive thinking. The inner function find does the actual recursing. It takes 2 arguments, the current number and the string that records how we reach this number. If it finds a solution, it returns a string that shows how to get to the target. If it can find no solution starting from this number, it returns null. To do this, the function performs one of three actions. If the current number is the target number, the current history is a way to reach that target, so it is returned. If the current number is greater than the target, there's no sense in further exploring this branch because both adding and multiplying will only make the number bigger, so it returns null. Finally, if we're still below the target number, the function tries both possible paths that start from the current number by calling itself twice, once for addition and once for multiplication. If the first call returns something that's not null, it is returned. Otherwise, the second call is returned regardless of whether it produces a string or null. To better understand how this function produces the effect we're looking for, let's look at the calls to find that are made when searching for a solution for the number 13. The indentation indicates the depth of the call stack. The first time find is called, the function starts by calling itself to explore the solution that starts with 1 plus 5. That call will further recurse to explore every continued solution that doesn't yield a number less than or equal to the target number. Since it doesn't find one that hits that target, it returns null back to the first call. There, the question mark operator causes the call to explore 1 times 3 to happen. This search has more luck. Its recursive call, through yet another recursive call, hits upon the target number. That innermost call returns a string, and each of the question mark operators in the intermediate call passes that string along, ultimately returning the solution. Growing functions. There are two more or less natural ways for functions to be introduced into programs. The first occurs when you find yourself writing similar code multiple times. You prefer not to do that, as having more code means more space for mistakes to hide and more material to read for people trying to understand the program. So you take the repeated functionality, find a good name for it, and put it in a function. The second way is that you find some functionality that you haven't written yet that sounds like it deserves its own function. You start by naming the function and then write its body. You might even start writing code that uses the function before you actually define the function itself. How difficult it is to find a good name for a function that is a good indication of how clear a concept it is that you're trying to wrap. Let's go through an example. We want to write a program that prints two numbers, the number of cows and chickens on a farm, with the words cows and chickens after them and zeros padded before both numbers so that they're always 3 digits long. This asks for a function of two arguments, the number of cows and the number of chickens. Let's get coding. Writing .length after a string expression will give us the length of that string. Thus, the while loop keeps adding zeros in front of the number strings until they are at least 3 characters long. Mission accomplished. But just as we were about to send the farmer the code along with a hefty invoice, she calls and tells us she's also started keeping pigs, and couldn't we please extend the software to also print pigs? We sure can, but just as we're in the process of copying and pasting those 4 lines one more time, we stop and reconsider. There has to be a better way. Here's our first attempt. It works, but the name print zero padded with label is a little awkward. It conflates 3 things, printing, zero padding, and adding a label into a single function. Instead of lifting out the repeated part of our program wholesale, let's try to pick out a single concept. A function with a nice obvious name like zeropad makes it easier for someone who reads the code to figure out what it does. Such a function is also useful in more situations than just this specific program. For example, you could use it to help print nicely aligned tables of numbers. How smart and versatile should our functions be? We could write anything from a terribly simple function that can only pad a number to be 3 characters wide to a complicated generalized number formatting system that handles fractional numbers, negative numbers, alignment of decimal dots, padding with different characters, and so on. A useful principle is to refrain from adding cleverness until you are absolutely sure you're going to need it. It can be tempting to write general frameworks for every bit of a functionality that you come across. Resist that urge. You won't get any real work done, but you'll be too busy writing code that you'll never use. Functions and side effects. Functions can be roughly divided into those that are called for their side effects and those that are called for their return value, although it is also possible to have both side effects and return a value. The first helper functions in the farm example, print zero padded with label, is called for its side effect. It prints a line. The second version, zeropad, is called for its return value. It is no coincidence that the second is more useful in more situations than the first. Functions that create values are easier to combine in new ways than functions that directly perform side effects. A pure function is a specific kind of value-producing function that not only has no side effects, but also doesn't rely on side effects from other code. For example, it doesn't read global bindings whose value might change. A pure function has the pleasant property that when called with the same arguments, it always produces the same value and doesn't do anything else. A call to such a function can be substituted by its return value without changing the meaning of the code. When you're not sure that a pure function is working correctly, you can test it by simply calling it and knowing that if it works in context, it will work in any context. Non-pure functions tend to require more scaffolding to test. Still, there's no need to feel bad when writing functions that are not pure. Side effects are often useful. There's no way to write a pure version of console log, for example, and console log is good to have. Some operations are also easier to express in an efficient way when we use side effects. Summary. This chapter taught you how to write your own functions. The function keyword, when used as an expression, can create a function value. When used as a statement, it can be used to declare a binding and give it a function as its value. Arrow functions are yet another way to create functions. A key part of understanding functions is understanding scopes. Each block creates a new scope. Parameters and bindings declared in a given scope are local and not visible from the outside. Bindings declared with var behave differently. They end up in the nearest function scope or the global scope. Separating the tasks your program performs into different functions is helpful. You won't have to repeat yourself as much, and functions can help organize a program by grouping code into pieces that do specific things. Exercises. Minimum. The previous chapter introduced a standard function math.min that returns its smallest argument. We can write a function like that ourselves now. Define the function min that takes 2 arguments and returns their minimum. Recursion. We've seen that we can use the modulo remainder operator to test whether a number is even or odd using modulo 2 to see whether it's divisible by 2. Here's another way to define whether a positive whole number is even or odd. 0 is even, 1 is odd. For any other number n, its evenness is the same as n minus 2. Define a recursive function isEven corresponding to this description. The function should accept a single parameter, a positive whole number, and return a boolean. Test it on 50 and 75. See how it behaves on -1. Why? Can you think of a way to fix this? Bean counting. You can get the nth character or letter from a string, and writing n after the string, for example string 2, the resulting value will be a string containing only one character, for example b. The first character has position 0, which causes the last one to be found at position string.length -1. In other words, a 2-character string has length 2, and its characters have positions 0 and 1. Write a function called countBs that takes a string as its only argument and returns a number that indicates how many uppercase B characters there are in the string. Next, write a function called countChar that behaves like countBs, except it takes a second argument that indicates the character that is to be counted, rather than counting only uppercase B characters. Rewrite countBs to make use of this new function.